Hi. In this video, I'm going to go over the inclined plane notes. So the question that guides our notes on this is how do you set up a problem where the object is on an inclined plane? So that would look like an object like this where it's on a sloped thing like a hill or something to that effect, or a ramp, and we're going to try to analyze the forces on it. So the easiest way to solve an inclined plane problem is to rotate your axes. So imagine we have a 5 kilogram block on a ramp that is inclined 40 degrees. So here's kind of the diagram of what that situation might look like. And here is what our force diagram would look like. We got our gravity straight down. We have the block is touching the ramp, so the ramp would apply a normal force perpendicular to it, which is going to put it at a bit of an angle. And we have the force of friction, which is parallel to the surface and directed, opposite up the hill. So what we want to do is basically change it so that the y direction is aligned with the normal force, and the x-axis is aligned with the ramp, basically the surface. Now, the reason we would want to do that is one, mathematically, it makes our lives easier because gravity is now the force. We need to break only gravity into its pieces, into use sine and cosine. We don't need to break the normal force and the force of friction into pieces. So mathematically, that just makes it easier. The other advantage is that if when we start to talk about objects that accelerate, it will accelerate in the x direction. And so that is also better because otherwise we'd have like an x and a y component of acceleration, which would be fairly terrible. So here's kind of the way to think about it. We start out with right our this blue x and y coordinate axes. That's the one that we're most familiar with, right? X is horizontal and y is vertical. And all we do is we just rotate this axis. So you just take where the x-axis usually points directly to the right, and you just rotate it up so that it points, up into the right, so that it follows the the ramp there. And then same thing with y. Y is going to rotate the same amount. So it used to point straight up and down. It now points kind of perpendicular to the surface. So what that means is in this case, we just rotate everything 40 degrees. You probably can't see it because it's too little, but that says 40 degrees right there. So, um, so what that does is our force diagram, gravity is the thing that gets broken into pieces. So here's gravity. Um, This angle right here is the same as the angle of the ramp. It's the same as this angle. And the reason is because basically, again, we rotated everything 40 degrees. So that's a 40 degrees rotation. That's a 40 degrees rotation. So therefore, that is also 40 degrees right there. And so the way to kind of think about this is when you draw your force diagram, that's the thing in red, right? Looks just like this one. And what you do is you go to break it into pieces, you just go opposite from the normal force, and then you make a right angle and you head towards the end of force of gravity. So this should be a right angle. Lots of times people want to continue it too far and then try to go across. Be careful you don't do that. Again, we want to make sure that the force of gravity is the hypotenuse of the triangle. So be very careful. Again, the right angle should be right here. That changes this part into mg cosine theta. The mg comes from the force of gravity. The cosine is because you're adjacent to the 40 degrees right here. And obviously theta is theta, right 40 degrees. This one, this is the part of gravity that's pulling it down the slope. So that's the part that makes it want to go that direction. And this part becomes mg, again, because of the force of gravity. Sine, because you're opposite from the 40-degree angle, theta, again, which would be 40 degrees. So let's go ahead and actually solve this example problem that we've set up. It doesn't have an example problem with this set of notes, but let's just go ahead and try to do that. So let's see here, push stuff this way a little bit. Okay. So let's assume for it doesn't say this, but let's assume that it's moving. It's either not moving or it's moving at a constant speed, which just means that we have balanced forces both, both in the x and y direction. So it's not really any different. We've, like I've gotten. If you think about our summing forces notes, we've done steps. You know, we've done step one, which is to draw a force diagram. We've done step two, which is to pick a coordinate system. We had to pick that rotated coordinate system. Then we did three, split any diagonal forces into the x and y components, right? We did that. And so then we're now to this step number four, add all the forces in the x direction and set it equal to the net force, which again, since we're assuming that it's not moving, our net force is 0. So we'll do that step. So we sum, let's see here, x direction is blue. Let me go with blue here. So I'm going to sum all my forces in the x direction. That's going to equal 0 because, again, we're not accelerating up and down. As usual, forces to the right minus forces to the left. So that would be force of friction minus the forces to the left. So again, we're now, instead of looking for horizontal forces, we're looking for forces that are aligned with our new x direction, which would be, this direction right here. So we're looking for things that are pointed up and to the right and versus down and down and to the left. So the other force would be this mg sine theta, so minus mg sine theta, which again, theta is 40 degrees for us. In this case, we're going to be looking for force of friction. We know m is 5, g is 9.8, and theta is 40. So we'll go ahead and add. Do that to both sides, right? So that is going to give us mg sine theta is equal to force of friction. That's going to be 5 kilograms times by 9.8 times by sine 40 degrees is equal to force of friction. Then simply type that into your calculator. 5 times by 9.8 times by sine 40 degrees. It's just going to give you 31.5 newtons. If we wanted to then figure out what the y direction is doing, right, then we just sum our forces in the y direction. If we sum our forces in the y direction, right, let's look at it. Our y direction is now, right, in this direction. So that's going to be normal force, which is up, mg cosine theta, which is down. So again, the block is not accelerating, well, in any direction, but specifically not right in the y direction, not kind of up and down. So that's going to give you, up would be the normal force minus this mg cosine theta. As last time, just like last time, add the mg cosine theta to the other side. So you get mg cosine theta equals normal force. Plug in the numbers. So 5 times by 9.8 times by cosine of 40 degrees is going to give you 37.5 newtons. And that's how you do this problem. Thank you for watching. Oh, you need to see it. Sorry, there it is. Okay, thank you for watching.